A little bit about dilations. This is our lesson for dilations. And the first thing I want to talk about is just ask you, when have you heard the word dilation? And maybe some of you have been to the eye doctor and they've talked about dilating your eye or checking to see if your eyes are dilating. And when doctors are doing that, looking for your eye to dilate, maybe many of you know that they're looking for the pupil in your eye to get bigger or smaller. So that's what a dilation is. It's the only transformation that changes the size of a figure. It doesn't change the shape. A triangle would still stay a triangle. It's just going to be a larger triangle. So instead of having congruent figures, you're going to have similar figures. They're going to have the same angles. They're going to have proportional sides, but they're going to be similar versus congruent versus exactly the same. So that being said, let's talk a little bit about dilations and kind of what they mean. I don't want you to necessarily read these definitions in here particularly, but a couple of things I want to point out in regards to this section right in here. So a dilation with a scale factor of k. Now I know this whole term scale factor is new, and so I want to talk about if you've heard like a model, like a scaled down model, or something that's not drawn to scale. Okay, so that's what we're talking about, the scale factor. In other words, when you have like a model plane, it takes an actual plane and it scales it down it uses a scale factor, and that means the dimensions have been scaled down by this particular factor. Okay, so that's what we're talking about. So we're going to either be scaling things up, making them larger, or scaling them down, making them smaller. So this is a really simplified version of like what architects may use when they're designing a building, and they have to create a smaller, scaled down version of the building they want to build to show people. So this is kind of like talking about what architects would actually use, but they would use a lot more detailed things than we're doing. But this is a good introduction to that type of thing. So an enlargement, or creating an image larger than the original, makes sense that the scale factor is going to be greater than 1, because if we're actually going to make something larger, we want to multiply it by a number that's larger than 1. And then a reduction, or an image that's smaller. Okay, if we want to take something to make it smaller, like if we want to take a real life-size building and scale it down to a model-size building, we would actually need to scale it down to a number that's less than 1. Now, just keep in mind, it has to be greater than 0, because we can't scale something down to a negative number. We could just like cut it and make it half the size or a tenth of the size or something like that, but we couldn't make it -2 of the size. So you can't really go negative. So if you wanted to make it exactly the same, then your scale factor would be 1, because 1 times anything is the same number. So greater than 1 would be an enlargement, and less than 1 would be something that would make it smaller. Okay, so we're going to only focus on the center of dilation is the origin. So kind of like we did all of our rotations around the origin, the center of dilation is also going to be around the origin. So that's just kind of an introduction. And here's the rule: the scale factor times the x coordinate and the scale factor times the y coordinate. So it's super, super easy for this rule. So when we go through and put all the rules on paper, you'll have everything you need to do some of these items. So I'm going to go ahead and we're going to look at the first example. If I can clear the ink, we're going to look at the first example down below on the paper, in the book. And the first example is just showing you how, not even any graphing, it's just taking the triangle, the points, the 0, 0, the 8, 0, and the 3, -2, and finding the new coordinates if we have a dilation with a scale factor of 4. So how easy this is going to be, I'm going to do this over here just to show you. My A is 0, 0, so my A prime would be 0 times 4, which is 0, and 0 times 4, which is also 0. So look, it doesn't even change. Doesn't even change. That point will not move, but some other points might. So my original B is 8, 0. So B prime scaled up would be 8 times 4, or 32, and 0 times 4, which is 0. Exactly what they have here. And then my C is also going to move. My C, the original C, is 3, negative 2. So I'm going to do C times 4, that's a dot for times, and negative 2 times 4. So C prime is going to be 12, negative 8. And that's what they have here. There we go. So that is the example, example 1. So what I'd like you to do to turn in today is I'm going to start you with example 2 down here. Here's the vertices, W, X, Y, Z. I'm going to do W and X with you, and I want you to turn in, type in the answers for Y prime and Z prime. You may not even need to watch this example, but here's what you need to turn in. One of the things you need to turn in for watching this video. So here's our original points. Find the new coordinates after a dilation with a scale factor of 2. So all we're going to do is we're going to do 2 times every X and 2 times every Y to get our new points. So I'm going to do W prime. So negative 2 times 2 is negative 4. And 4 times 2 is 8. We have to multiply both coordinates by the scale factor. So that means X prime is going to be 1 times 2, which is 2, and 4 times 2, which is 8. You do Y prime and Z prime and turn those in. Okay, I think you can get it. It's pretty easy. And let's go ahead and turn to the next page. Let's see. And let's look at 489 and the graphing. Now we're going to move into some graphing. Okay. So I'm going to do this one for you. Okay. I'm just going to do the got it problem as your example. So a figure has these vertices, so let's graph them. Negative 1, 1. That's point F. G is 1, 1. Okay. H is 2, negative 1. And I is negative 1, negative 1. Okay. Okay. I think so far so good. So I'm going to connect these and just bear with me on my drawing because I'm not real great with this thing. Okay, so we have a trapezoid. We almost have a rectangle. We have a trapezoid. And it wants us to do a scale factor of 3. So here's what I would like you to do. Let's find all the F primes first. So negative 1 times 3 is negative 3. And 1 times 3 is 3. Okay, G prime is 1 times 3 and 1 times 3. So that's just going to be 3, 3. Okay, H prime is going to be 2 times 3, 6, and negative 1 times 3, which is negative 3. And then I prime is going to be negative 1 times 3, both of those, so negative 3, negative 3. So let's graph those and see what they look like. So let's start with F. Negative 3, 1, 2, 3. Okay. G is 1, 2, 3, 1, 2, 3. Okay. H is 1, 2, 3, 4, 5, 6, 1, 2, 3. Oh, it's a scale factor of 3, so it should be getting quite a lot larger. And I is negative 3, negative 3. Oh, I didn't mark all these. F prime, G prime, H prime, I prime. So now again, bear with me. It's not going to be the prettiest. Okay. But there's going to be one other thing I want to point out to you on this. Okay. All right. Notice the length of the side from F to G. Okay. The length of this original shape is 2. The length of this original side of this shape is 2. Now let's look at F prime and G prime. What do you think? If our scale factor is 3, if the side length is 2, just make a guess before counting. I mean, look at it. Side length. It's probably going to be 6. Let's count. 1, 2, 3, 4, 5, 6. Absolutely. So not only do my points get multiplied by 3, but the lengths of the sides are also 3 greater. So this is a side length of 2. So we have 2, 4, 6. This is a side length of 3, so this is going to be a side length of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So just kind of wanted to point that out to you, okay? So let's go ahead and look at the next example. And I want to point out, this one's kind of an interesting one. It's a word problem, and I know you love those. Through a microscope, the image of a grain of sand with a 0.25 millimeter diameter appears to have a diameter of 11.25 millimeters. So here's the grain of sand, the actual measurement, but it appears to have this measurement. So what is the scale factor? So we're taking a small grain of sand and we're making it larger because that's what microscopes do. They take something and they make the image larger so that you can look at it. So you can actually look at a very small object and it looks larger. But what's the scale factor? What is that microscope? How much is it scaling it up for us to look at? So I want you to notice that what they have first, we're going from small to big. So whichever one is the one you're changing to. So what I want to say is this is what you're scaling to. Whether you're scaling up or down, your top number is what you scale to. Okay? And then your bottom number is always your original. Always. Okay? So what you're scaling to divided by your original will equal your scale factor. Okay? So what we're going to is 11.25. That's what we are scaling to. Our original size is 0.25. When you divide that out, you get 45. So therefore, our scale factor is 45. So let's do an example like that together. And then you can stop the homework or stop the video. Okay? So let's try this one. Oh, it's fractions. That's horrible. We're going to turn these fractions into some decimals, so that'll make it easier. So Lucas wants to enlarge. So he wants to take a picture and make it bigger. He wants to take a 3 by 5 inch photo. So here's my original, okay, width and length, and we're going to scale it up to a 7.5 by 12.5. Okay, so let's do both of these. Let's do our length and our width and make sure we get the same scale factor. So let's take our shorter side first, our 7.5 and our 3. So this is what we're scaling to, okay? So we're scaling to this, so this is going to go on top, okay? So 7.5 on top, and my original is 3. So divide that out. So 7.5 divided by 3, you should divide that out, okay? And then let's go ahead and set up my next one, which is going to be 12.5. We're just going to check. We should get the same answer. So my length, 12.5, is my scaling to, divided by my original. So 12.5 divided by 5, and 7.5 divided by 3. And you guys should get 2.5 as your scale factor. Now that is not inches. Okay, this is not a dimension. This is what we multiplied the 3 and the 5 by to get to 7.5 and 12.5. So we scaled it. We made it 2.5 times larger. We made that picture 2.5 times larger. All right, you guys can stop the video and prepare to do your assignment. And that is all I'm going to have you guys type in is those other 2 points from a while back.